So let's continue from where we left off in the first lecture. We talked about FDM, PDM, CDMA, OFDMA, NOMA, HAMUX, and then we said that HAMUX is one of the new developed technologies that we developed here at Wislabi in order to make sure that there is no inter-user interference whatsoever. Each user will get the full bandwidth of the base station and the full data rate and the full speed. The number of users will not affect this internet speed whatsoever. But we noticed that in HAMUX, the auxiliary signal we add to our users' data is dependent on the channel matrices between the transmitter antennas and the receiver antennas and the data of the users itself. So we would rather prefer to have something that's dependent on the channel only so that we can reduce the complexity a little bit and use something that's not additive, something that's multiplicative, as it's more friendly to linear processing and processing in telecommunication in general. So what we are going to do is we will erase all these equations related to HAMUX multiplexing technique and come up with a new technique, with a new architecture and transmitter design that can solve the previous issues related to NOMA, HAMUX, and other techniques. So let's begin with this new technique that we will name it together what? ZIMUX, zero interference multiplexing. So we have now HAMUX, and now we will talk about ZIMUX. So what's ZIMUX now? And there will be a homework as well related to ZIMUX. Okay, each technique we give a homework. And all the homeworks are optional, not mandatory. If you solve them, you get bonus. If you don't solve them, it's okay, I will give you the solution. Yes, but if you push yourself, it will be really great. Okay, we have then, in this technique, we have base station. This is tower. That got two antennas. For simplicity, we always start with two antennas, but for generalization, we can do it for multiple antennas, okay? 10, 100, whatever. And we have two users here, user 1, user 2, and this user 1 receives Y1 signal and user 2 receives Y2 signal. Sometimes we call them user equipment 1, user equipment 2, or device 1, device 2. And this is antenna 1, this is antenna 2, and we assume to be using OFDM. OFDM is OFDM not as a multiplexing technique, as a waveform technique. So people sometimes confuse between OFDM and OFDMA. OFDMA is a multiplexing technique that distributes resources on users based on their needs. And the resources here are time and overlapping frequency, subcarrier frequencies. But here we are using OFDM as a waveform so that we can do all our processing, whether at the transmitter or at the receiver, in the frequency domain, not in the time domain. And why do we prefer to do our processing in the frequency domain? Because we usually get easier equalization, which is the process that gets rid of the effect of friction between the transmitter and receiver. And we get some additional advantages, especially when you are designing something at the transmitter. So here is the catch in this technique. We will not use additive auxiliary signals or anything that's on top of something, but rather we will use something like precoders, new type of precoders that are capable of removing the inter-user interference in a multi-user network. So how is the design will look like? So the design will look like this. Let me erase these antennas a little bit. So we have X1, X2 data, X1 and X2, X1 for user 1, X2 for user 2, and we make them go through a precoder here So this block over here is decoder 1, and we have I50 block, and then we have the CP block, the addition of CP cyclic prefix, and then we have the digital to analog DAC, and we have the RF chain here. After that, you can put the RF chain, the radio, and go to the antenna. So this is the for X1. So we are putting a decoder here. And for X2, we are putting another decoder. Decoder, let's call it B2, or I want to make a space because we'll use 4 recorders here. Okay, this is B2. It goes to an I50 block like the one above it. CB block, and then DAC, and then to the antenna. And this antenna 1, this is antenna 2. And as you know, the signal goes, this is user 1, this is user 2, he's interested in U1, U2, and this is the signal. And the signal goes something like this. If from antenna 1 to both, user 1 and user 2, and if from antenna 2 to both, user 1 and user 2. And we name the channels. This is H11, H11, and this is H12, and this H21, exactly. 2, we said this for the user, and the other for the antenna, and this H22, excellent. H22. And we will add another clever modification to the system model over at the transmitter. We will take this data over here. This data over here, we will take it and make it pass through another precoder. We call it B3. And this goes to the I50 of the first user's data. Okay? We take user 2 data, we precode it with another third precoder and make it go to the I50 of the first user's data chain. This is clever like move. We will know why we need to do this. And we do the same for X1. X1, we take it from here, we take the data from here, and we make it pass through another precoder B4, and then let it go to the I50. Of the I50 of what? Of the second user data. And then you have this system then. How do you model it here? Can you, what's the procedure here? Write the equations for Y1 and Y2. What will it be? You considering this system. So let's do it together. So for Y1, what happens for Y1? You get some data from here, and data from here, you need to add it here. So let's together write it, yes? So Y1 equal to H11, assume this to be something like V1 here and V2 here. And before we start, what's V? If I tell you what's the signal here, V1, before we write what Y1 is and Y2 is, what's V1 here after I50? Can you tell me what's